Welcome back. In the last lecture, you looked over some models in which you have seen some geomorphic landforms and geological structures, as well as some kinds of different topography like karst topography, some volcanic models, as well as some models related to thrust and faulting, and how the horst and gravens are formed and how they look alike on the surface, and how to map some region with the help of identifying some geological structures like folds, faults and joints, unconformities, etc. So, you also learned about the strike and dip and taking measurements of the strike and dip on a fault plane, fault zone, or on the limbs of a fold, so that we can use this information to map an area, to know the slope, the kind of topography and relief, ground relief of a particular region. So, this all information we can use to model some area in terms of having x, y, z coordinate, or in terms of the elevation. Okay. So, elevation is the parameter which gives us the relief on the topography. In this lecture, we are going to start with some geomorphic landforms over the black and white photographs. Okay. So, first we will go through the black and white photographs, aerial and satellite, then we will move to some color photos, how they look alike on the surface. So, as in this case, you are able to see this fluvial landform, fluvial topography, and where you can easily identify some most prominent features, like here is a ridge which is moving like this, okay, and there are some hills, and there is dissection of the ridges and hills. This dissection may be due to some fluvial source like some surface runoff, or due to precipitation, and due to which there are number of gullies are formed. Okay, like this. We can map all these features with the help of this photograph, as well as we are also looking over some flat topped small features which are also known as butte, and this ridge which is continuous on this photograph from this point to this point, it is having a steep slope on its both sides, but this region A and B, this represents gentler slope. Okay. So, this area is gentler and this is steep, and that is why, because there is surface runoff, and that may be from a source, fluvial source like a river, like here we are looking at a major channel, and at this place also we are having a major channel. So, this may provide some surface runoff to this region as well as precipitation also. So, that is why there are number of gullies. Note that there no single large stream crosses any of these surfaces. Okay. Instead of that, hundreds of small gullies can be seen on this photo. The next photo is the other side of this region, where you again note down the C and D part of this area. C and D, so these are representing the gentler slopes, gently sloping surfaces, gently sloping surfaces. And other part is that there are some hilly terrain and some partlier area of the remaining hilly terrain which might have eroded by fluvial sources like surface runoff from a river or anything. So these parts are the leftover parts of the previous rocky terrain at this area. And here we can note down that a single large channel kind of feature is very prominent here. Okay. Here also we can notice some changes in the slopes downward. Okay. And where we get such kind of topographic relief, we can also find some radial drainage patterns. Okay. So how they look alike you will see on the other photographs. In this photo you can quantify the areas which are having a very flat top terrain like this and this part B. Okay. And other thing that is important, it shows the asymmetry of the ridges as well as V-shaped notches, and there are gently tapering nose at the apex of plunging fold. So where are the plunging fold? I already explained you with the help of models how the plunging folds are look like on the photographs. Like if you are having a plunging fold, so this will be your core area of a fold. Okay, the core area, and its surface will be tapering at its end. Okay. So what is the meaning of that? That it has, this is the hinge part of this area, the point of maximum curvature. So this line is actually having a slope. This is not straight as it should be in a case of normal fold. Okay. So normal fold will look like this and it will go parallelly with reference to its limbs and its center. Okay. So this height varies at a very smaller scale, whereas in this case, as you know that this is the axial plane of this fold and this is the axis and this is the hinge part. So this fold is plunging over here. So if suppose there is only a cross section left over on some ground, so in that case you will only find these kind of features. Not the complete fold, because the only cross section of this fold is left out. Why? Because all these things has been eroded. Okay. So only what you are looking from the surface, when we see, as in case of the models, when we look a fold in from the front side, we can look on its cross section and we can have the information of its bedding planes and the thickness of the limbs, etc., and their orientation. But when we look this fold from the surface, then it is not possible to look on this section. So, in that case we will look only this part. So, when the top part which is exposed above the land surface, when this part is eroded, so in that case only some limbs are left over like this. So, this is the top section of the limbs. So, here in this case you are getting these plunging folds. Okay. Another thing, where the beds that dip in only one direction make either a homoclinal ridge or homoclinal valleys. Okay. So, in this case you can look that there is a linear ridge like feature and streams are coming, and these are the tributaries actually which are joining the main channel. Okay. So, most probably you will find the dendritic drainage pattern in such regions, dendritic drainage pattern. So, if we talk about the homoclinal ridges or homoclinal fold, so this in this case this fold is a homoclinal fold because the both limbs of this fold are dipping at the same angle. So, okay, both the limbs are dipping at the same angle. This angle may be from the axial plane also. You can take the reference of the axial plane here. Okay. So, these many things you can identify on a particular image. The next thing is the beds that dip in more than one direction make anticlinal ridges, valleys or synclinal valleys. So, where there are combination of two folds in a series, so one of that must be an anticline, another should be syncline. So, in this case when you get the a higher part of the beds on the core section of a fold, so it means this fold must be anticline. Okay, anticline fold. So, in case when there is no section or there is a depression kind of thing developed in between the limbs of a fold or a center of a fold, in that case it may be a synclinal fold. Okay. So, whenever you will find the two folds in a series, so in that case one will be a syncline and anticlinal. So, here you get the plunging syncline and plunging anticline, plunging syncline and plunging anticline. In this photograph you will be able to map some faults which has affected the terrain, and the configuration along the eastern side of this terrain is shown in this vertical aerial photograph, where most of the things you can identify very easily, like this cutting of the or dissection of the geomorphic landforms. So, these features obviously represents the faults. Okay. Suppose here is a stream flowing like this, and then it is getting diverted along this fault and then coming like this. So, this stream got diverted due to this faulting pattern, as in case of Taksal fault, where streams got deflected due to strike slip faulting. So, what kind of fault that was? That was the lateral right lateral strike slip fault. right lateral strike slip fault. And what happened there? So suppose this is the fault, this is the fault line. So streams are coming like this, and when they cross this fault line or the fault zone, so then they diverted in terms of their flowing path. Okay. So because the sense of motion on this fault is like this block is moving in this direction and this block in this direction. So this is very easy to identify a sense of motion on the strike slip fault. So how to identify it? Suppose this is an strike slip fault. Okay. So this is the right block and this is the left block. Okay. So if the right block is coming towards me, then it will be right lateral strike slip fault. If the left block is coming towards me, so it will be left lateral strike slip fault. Right lateral strike slip fault is termed as dextral fault also, and left lateral strike slip fault is also termed as sinistral fault. Remember that? So here also this is the strike slip fault, and the streams are deflected when they cross this fault. You will find some streams which cross this fault but do not show much deflection. It means that they originated after the last event on this fault. Okay. So obviously this fault move during an earthquake or event on this fault. The blocks move when there is an event on this fault. So whenever there is an event, there will be some strike slip motion. So suppose in one event it moved around 1 meter, in two events suppose 2 meter. So it will show, we can also detect the number of events on a fault by quantifying the deflection pattern of different streams. Like this stream is showing the maximum deflection of around 3 meter, this is showing a deflection of 2 meter, it is showing the deflection of 1 meter. So it means that this is the oldest stream which generated along this terrain and flowed through this fault. This is the younger, and this is the younger than this. Suppose this is stream number 1, this is stream number 2, this is stream number 3, and this is stream number 4. Because this shows the maximum deflection, it will be your oldest stream which developed on this terrain and crosses the fault. Okay, that's why it shows the maximum deflection. This is it shows a deflection of 2 meter, which is somewhat lesser than the 3 meter. So that's why this is the younger stream than stream number 1, and then similarly stream number 3 is younger than stream number 2, while stream number 4 is the youngest stream because it does not show any deflection on it. Okay. So this was about Taksal fault, which was a strike slip fault. This fault is also seemed to me like a strike slip fault because it shows some deflection in the streams. Here is another fault, the linear feature. Okay. There is some other kind of feature which is matching with the pattern of a meandering river. Okay. So meandering channel flow like this. Okay. In between here you will be able to look over some kind of fan like features which may be alluvial fan. So at the basic level of the interpretation, you can at least judge that because these features are nearby a river, very close to this river, they might be related to an alluvial terrain or alluvial plain. Okay, so alluvial fan. This whole plain is called the alluvial plain. Okay, so these fan like features are also termed as alluvial fan. Here very clearly dissected hills are shown, which can be mapped very easily on this photograph. Okay, this may be because of a river channel which is flowing from here to here. Okay, so whenever there is a supply of huge water quantity, so there will be lots of erosion on the terrain, which depends on the slope of the topography. So suppose topographic slope is in this direction, so there will be more erosion on this side. However, you will not see any more erosion on this side, very less erosion, and this is highly eroded terrain. Okay, so this is very close to coastal region also, so that may be a reason that some amount of water is drained from the sea part, and these may be forming the tidal estuary or channels which are having the maximum input of water during the high tides also. So this is the extended stereo pair. It is mainly showing the gullying and collapse of the escarpment. So gullies you know very well. So these very dense features, okay, which converts a land into a bad land topography. Are mainly the gullies. So gullies erosion occurs when there are number of major channels flowing across a topography, and due to which they caused the erosion and cross cutting of the structural features, and they may also do some undercutting due to incision during some events when there is uplift of this region, so that this river will maintain the base level. Because suppose a river is flowing like this, this is the cross channel of a river, this is the highest water level here, and this is the topographic slope. Okay, so suppose there is an uplift, so what will happen? The topography is at its own level, but the river is flowing from some upland area, okay, and going towards a lowland region. So suppose in this case this is the highly elevated region, plateau kind of thing or escarpment, and this is some planar landforms like alluvial plain or flood plain, extensive flood plain formed by the rivers. So what will happen, because a river is flowing from higher ground to lower ground, where this axis represents the distance and this axis represents the elevation. So what will happen if there is somewhere uplift in a topography, uplift in this region? So what river will do? River will maintain its base level, because this region is got uplifted due to some earthquake or so, or movement of some fault here, some block has moved up, due to which this topography is showing some high relief. So in that case the river will maintain its base level, so it will undercut or incised beneath this topography. Okay, so that is called the maintaining the base level of erosion. So this is, in this case, this is the base level of erosion for this river, base level. Okay, so when it will maintain some base level due to uplift, so it will go down and undercut the bedrock. Okay, so this is this image. On this image we can easily map this region, and we can classify the terrain on the basis of the fluvial channels and the extensive floodplains on both the sides. Of course, there are some dissected hills or ridges in between these floodplain regions, and due to which there are number of gullies are formed, okay, and converted this land into a badland topography. On this image is very important, and please try to understand what is shown on this image. First, try to identify the most prominent features always. So on this image we will go with this feature. Okay, so I will say that this is the most prominent feature in my image. Another thing, I can also mark here that there is some ridges or maybe kind of some faulting. So this fault is very prominent. We don't have any confusion in interpreting it, this lineament, as a fault. Because why? Because this is cross cutting the fluvial terrain, and this is flowing and bisecting the drainage patterns, and there is a sense of movement in between these two kind of drainage basins. So there is one drainage basin and this is another drainage basin, and then you will find another drainage basin. So here you can easily identify that there are streams, and these are showing the dendritic patterns. Okay, I don't need to explain it because I have already explained in the last lectures. Okay, so dendritic drainage patterns on this side also and on this side also, a very clear cut tree like branching and radiating features. Okay, so these are the drainage patterns, and here a very prominent alluvial fan is shown. Okay, alluvial fan is when the river debouches somewhere in a sea or some lowland from coming from an upland region. So then it will form a alluvial fan at the base. So this is base of this region. So this is the upland, and this is the, toward this side there is plainer areas. So this is the alluvial fan, and so this fault is cross cutting the topography and bisecting this drainage pattern. So this is, we can say that this must be this fault is showing a large slip, which may be a dip slip or a strike slip, but there is dissection of the topography on both the sides. So that's why this fault shows the maximum slip. Okay, so we have another image, again the extended is stereo pair. Stereo pair is what, when we take images of a same area by moving through an aircraft or a satellite, and the two images which will have the 60% overlap or so, those images are called the stereo pair. This was explained in the first part of this course. 60% overlap is the standard overlap. However, there may be some other numbers which may be preferred for different kind of purposes, different kind of studies also. So here on this image you will see again the badland topography, and it is from the Dakotas, USA. And how the badland are formed, this I explained in the last slide. So this is also showing some rivers and gullies, erosions. So this land has converted into a badland which should not be preferred for some construction purpose or for putting some structures like tunnels or anything, some railway lines, okay, some dams. So these kind of sites should not be preferred. The other sites similar to badland topography is your karst topography, or the topography having the faulted and folded terrain or jointed terrain, okay. So these all kinds of topographies are not favorable for the construction purposes. This is again an extended stereo pair showing erosional features in the Thaapu Busai area of Lesotho, and the whitish part affected by the scarp collapse erosion, okay. When you will become a photo interpreter or an experienced photogeologist, then you can see these images in greater details, okay, because you will have the idea of topography, because when you have the field experience or some experience of different kind of landforms, when you have been where you have been physically there to study different kind of landforms, or if you have been interpreting these images for a longer time, then it will be easier for you to identify all these structures, landforms and settlements, and you can use these kind of photographs and to map some area and to make their use for the land use purpose. This is showing the ground view of an area affected by the scarp collapse again, okay. So the erosion at its base, and only here the rock is left, and that is wetted by the emerging groundwater. So but these kind of things you can only identify when you have the inside view of an area, otherwise it is difficult to interpret these kind of things, okay, because these things are related to some political information as well as some geographical information and some kind of geological information of a particular region. This is a very fascinating image that shows the accelerated linear erosion in the Chama Valley, and another part is this is showing the retrogressive erosion on the steep slopes, okay. So this is a valley. If you take the profile from here, from point A to B, you will find something like V shaped. Here also the cross section C to D will give you a V shaped valley, okay, and this is showing the intensive erosion, as well as you can also see some kind of linear features, okay. which are basically the parallel drainage pattern coming and joining this main channel flowing through this valley, the Chama valley. Okay. So, here you are able to look at the parallel drainage pattern. Again, we will quickly move through these images, which is again showing the Chama valley, and here you can map this is stream, okay, which is showing some meander at this place, and there are some sandbars inside. So, this is basically a braided channel where you are having braid bars inside this, okay, some kind of sand islands, and on the both sides you are looking at the parallel drainage patterns. So, let's look at some folded terrains on the black and white or gray scale aerial photographs. Here you can see that this topographic expression is showing the folded strata, okay. This is from the Spence. So, this is showing the folded strata where you can find some these plateau like features, okay. So, these are actually representing the zigzag pattern of this terrain, okay. So, when you see the contour map of this region, you will have a clear idea that yes, there is some tectonic landform over here. Like here, a fault is cutting this terrain and dividing the region of alluvial plain from the folded terrain, okay. So, on the left side of this fault, you will find the alluvial plain and lots of streams, very dense stream pattern, and due to which there is gully erosion. Inside also you will be able to map a very good zigzag folded terrain, okay. Similarly, on the other photograph you will find the folded stratas. So, how the surface expression of the folded strata is, you can see here, okay. So, from the space or from the sky, you can only view the outcrop pattern. Like if there is erosion of the superficial matter of a fold, then you will find only the limbs connection on the surface, okay, which is the cross section actually. Another image that is also showing the folded strata, a very beautiful image which classify the folding pattern as well as the hinges and limbs and the cores of the fold. So, this is the center of this fold, okay, and here this fold represents another center, and here is another connection between the folds, okay. So, you can easily identify all kinds of tectonic elements on a photograph. Again, a folded terrain, a very clear cut relationship between the hinges and the limbs. You can even quantify the thickness of the limbs on this photograph, okay. This is a huge fold, that is why it is showing the extensive limbs running across the topography, okay. So, based on this you can also map the topographic slope, where should be the the relief pattern going downwards. Okay, so these expressions showing the faulted and jointed terrain. Okay, where don't go on this line, because these lines are showing the mosaic of this photograph. So here you can see that a fold is coming like this, which is delimited here and end up here. Okay, and this feature is very prominent on this image. This is actually a kind of reverse fault, where this part has come up and this part is down, this part is up. Okay, and there are joints in between this terrain. Okay, number of joints, and here are some folds. So you can map all the tectonic features on this map, this photo. Similarly, this photo shows some joints and faults and the streams, how they are going and connecting and cross cutting this fold. This is the limb of the fold, and the streams are flowing across the topographic relief which has been built up by the folding. Okay, this image shows a very typical expression of a volcanic cone, where you can see actually this is a stereo pair. So up to this there is photograph number 1 and this is photograph number 2, and this is the overlapping part. So this part is also covered on this photograph. This is the overlapping part. Okay, so when we look over this with the help of a stereoscope, so then we can see this volcanic cone in 3D, which has been explained very well in the first part of this course. And you can also see here the radial patterns of these streams radiating outward from the volcanic cone. This is the crater of the volcano. Okay, and vent is going through this inside the earth, from where lava erupt, and here you can also see some lava flows. So this blackish part is basically showing the lava flows, which is limited up to this extent. Okay, so now you can see that from just looking from the air on a region, at a region, we can define the extent of lava flow and many things which are related to hazard mapping or zonation, and to present some land for different kind of construction purposes, or to decide how to use this land. In the last, I would like to make sure that you just recall this information. Okay, you might have learned it somewhere else or some other course also, but in the first part I remember this information was shared with you. So this image is showing different kinds of drainage patterns. Okay, where this is the most common dendritic drainage pattern. Okay, this is annular, this is subdendritic, like when there are some joints or faulted terrain. So dendritic pattern will follow, the main stream will follow the zone of the fault or the joint. So in that case you will find a dendritic pattern, but with some parallel streams. This is trellis, this is angulate pattern, this is parallel to subparallel, this is acute parallel, means parallel drainage pattern, this is rectangular. These are also common to faulted and jointed topography. And this is radial pattern, as I explained, in case of a volcano. Volcanic cone or some domal structure, you will find the streams radiating outward from the center. Okay, so these are the main types of drainage patterns which you should remember, and we will use it for our practical purpose, and you have to identify it, and we can also give you some image in the exam where you have to identify different types of drainage patterns. Okay, we will continue in the next lecture with some color photographs, and with the help of Google Earth images I will explain all these features, how they look like in real on the surface of the earth. Thank you so much.